Assalamualaikum and a very good day to everyone. Today I'll be talking about basic principle of ultrasonography. Okay, so let's move on. So my lecture outline will be the introduction, basics of ultrasound, transducers, modes of ultrasound, and ultrasound knobology. Okay, so this introduction I will telling about working definitions of ultrasonography, uses of ultrasonography in clinical work, and we'll move on to how the ultrasound works, details on the wavelengths and frequency and interaction of ultrasound with tissues and artifacts. And then we move on to types of transducer and how to clinically use them and care of transducers. Basics of transducers, movement and imaging planes, and several modes of ultrasound and ultrasound knobology. Okay. So for introduction, what we are doing in the ICU actually in our daily life is point of care ultrasonography, in which we bring the ultrasound machine to the patient. Okay, so ultrasonography is the study of using the ultrasound for diagnostic purpose, therapeutic, and the ultrasonography itself done by the treating clinician attending the patient at the point where the patient is being treated. Okay, so this is very different and in contrast to consultative ultrasonography, where it is also ultrasonography. It is most of the time is diagnostic and can be therapeutic depending on the situation. And it is done by the specialist or consultant radiologist referred by the treating clinician. Okay, and it's done at the radiology department. This is where we bring them patient to the ultrasound machine. Okay, so what we do in the ICU is that we bring the ultrasound machine to the patient, and the difference is that we are the one who do the point of care ultrasonography, while the consultative is that we are asking the radiologist to do the ultrasonography. Okay, consultative ultrasonography also includes echocardiography done by cardiologists. Okay, so where are the points at where the patient being treated? It can be emergency department, it can be in the normal wards, medical emergency wards. You can even bring the ultrasound in ambulance call, attending the patient at home. If you have the small devices, okay, and you can also bring it to the remote village and some mountainous region. You can bring a very small ultrasound for you to use for the patient. But the point that we are talking now is the patient. We bring the ultrasound machine to the patient in intensive care unit. Okay, so for everything, you must know basics of ultrasonography. Okay, so to begin with, how does it work? Okay, so to understand how does ultrasound work, you need to know about sound and generating ultrasound. Okay, sound is the most basic principle for ultrasonography and generating of the ultrasound. And directing and manipulating ultrasound wave is the heart of ultrasonography. Not only you have to know about sound, you have to generate the ultrasound, and by directing and manipulating this ultrasound wave is the basis of ultrasonography. So when you direct and manipulate the ultrasound wave, you want to target and to the tissues, the different tissues densities reflected it back to the probe and analyzed by the probe is what will produce the images. Okay, so and then when the images have been interpreted via the computer by the ultrasound machine, the different time delay of reflection of sound wave caused by different tissues in the body will be interpreted differently and shown with different levels of echogenicity in the monitor, because you have different tissues and it will show different echogenicity, black and white. And then when they interpreted the reflected sound, they will show the sound reflected in the form of images of black and white. Okay, so what is the physics of sound? Okay, sound can be explained via physics and human physiology. So in terms of physics, sound is a vibration energy caused by vibration of atoms in a substance. When we hit something, okay, when we hit something, like you hit the table, will cause a sound. It will cause a vibration of atoms inside the table, and it will cause a vibration of the atom, and will in this vibration energy is actually is sound. Okay, so how do we generate sound? Energy needed to initially cause vibration of atoms. Energy is needed to initially cause the vibration of atoms. The source of initiation can be kinetic, like hitting drums, or electric, like vibrating objects using electric energy. Okay, sound can be propagated through mediums. The closer the atoms, means like solid, the better the propagation of sound. Okay, so does solid better than liquid and better than air in terms of propagation of sound. Vacuum in the space, outer space, will not propagate sound because there is no atoms to conduct the vibration. So in terms of physiology of sound, in contrast to the physics, sound is reception of acoustic wave caused by vibration energy, the physics, by the ear, and perception by the brain. What kind of sound can we hear? Human can hear sound with the frequency between 20 Hertz and 20,000 Hertz. So there is this term of subsonic and ultrasonic. Subsonic and ultrasonic is the sound frequency outside the range of frequency of sound human able to hear. Subsonic is sound of less than 20 Hertz, and ultrasonic is sound of more than 20,000 Hertz frequency. Okay, so clinical ultrasonography is based on the manipulation of the physics of sound energy, the vibration energy. Okay, so not so much of the physiology of sound. It's more of towards using the physics of ultrasound, physics of sound, manipulated it, and then translated into clinical ultrasonography. Okay, so first we need to generate sound. The generation of sound is generated via electrifying the piezoelectric crystal on the probe, and we need to direct the sound. Directing the pulse or ultrasound can be done via arrangement of crystal. So not only we need to generate the sound, we need to focus it and concentrate the sound to go to the tissues that we want, to the target of area of interest we want. And once the ultrasound hit the tissues, there will be reflections in different tissues. Okay, so the sound will be reflected back towards the probe, and there will be a reflection delay. Okay, because tissues in our body have different densities and different makeup, water, solid, and so on. So once the reflection is generated and directed towards the tissue, the reflection will, with different delays, with different from different tissues, will come back to the probe, and the probe will receive it, and it will analysis of reflection. Okay, so reflected sound with different delays interpreted with different echogenicity to produce image. Okay, so we generate the sound, we need to concentrate and direct the sound, we need to receive the reflection delay. Because of there is delay between different tissues, that's why we can see different shades of white and black and different shades of gray. Okay, so analysis of reflection, once the reflected sound is received back by the probe, and the machine will analyze to produce image. Okay, so the basics of ultrasound is the piezoelectric crystal emits ultrasound wave. It will fall on the tissues of the body, and the ultrasound wave will be reflected back from the organ into the probe. The probe will receive it and send to the machine, and the machine will create the ultrasound image on the screen. So the more details on how it works is that application of an electric current like this to the crystal cause the crystal to vibrate. Okay, and thus generate ultrasound wave. This is electrical current, this is the vibration to generate ultrasound wave. The reflected ultrasound wave, when the ultrasound wave hit the tissues, the sound wave will be reflected back, okay, and hit the crystal, causing it to vibrate again, and it vice versa, on the other way around, the vibration will cause the piezoelectric to vibrate, and it will cause the generation of electrical energy, and the electrical energy will be received by the ultrasound machine processor, and it will be processed to produce image. Okay, so when we talk about wavelength and frequency, sound is constructed in waveform, okay, positive and negative deflection. So the shorter the wavelength of the ultrasound, means higher the frequency. Okay, the length of one wave is from one similar point to the other similar point. This is one wavelength. Okay, so sound with a long wavelength have a lower frequency, means the shorter the length of the wave, the more wave will occur, the more frequent wave will occur, means the higher frequency, the more frequent the wave will occur. You see, in one snapshot of the same time frame, you can have 1, 2, 3, 4, 5 frequent, the more frequent wave compared to this longer wavelength, 1, 2, 3 wave only. Why is this important regarding of wavelength and frequency? Is because that in ultrasound, when we talk about different types of probes and different type of transducer, like I said, we generate the sound. We want to manipulate the sound to get what we want. Okay, depends on clinical application. Okay, so when the different type of probe have different usability and clinical use in the ICU. Okay, such as phase array or echo probe, curvilinear or abdominal probe, and linear probe. So they are designed in such a way they have different types of frequency. Okay, so when the frequency from low frequency to high frequency, you can see the lower the frequency, the higher the penetration. Okay, so as you can see, when you move from lower frequency to high frequency, the resolution also increase. Okay, so the linear probe, the one that we use to insert lines, okay, it's a linear probe. It's between 5 to 15 megahertz. So the higher the frequency increase, the better the resolution. However, when you get a better resolution, that means your image will be better, more sharp, and can distinguish between one point to another point better. However, it will suffer from a lack of penetration. The penetration will drop dramatically as the resolution increase. Okay, I will show you later. So this is the inverse relation between frequency, resolution, and penetration. So as the frequency increase, resolution and image sharpness improve, but the penetration is reduced. That means you cannot scan a deeper structure in the body like abdomen using linear probe. Okay, so vice versa, if you use curvilinear probe to have a good penetration of the abdomen, you cannot get a very sharp, clear picture. You cannot differentiate between one small point to another small points in the ultrasound. Okay. So resolution like this, low resolution, but high resolution is good picture. Okay. So example of high resolution image in with a high frequency ultrasound is like this. So you can see very markedly, very good picture means really very good resolution means you can differentiate one point to another point. Okay, small point, small muscle structure can be seen, nerve structure, the muscle nerve bundles can be seen clearly from one another. Okay, so this is good application for good probes to be used for like a regional block or vascular access and so on. So as you can see here, the depth is quite narrow. It cannot scan very deep structure. Okay, so typically it's only about 3 to 4 cm depth that we can produce these very high quality resolution images. So as compared to a curvilinear probe, which has a very low frequency, you can have good penetration, can view deeper structure. However, resolution will reduce. Okay, so the typical depth will be 15 to 20 centimeter. Okay, moving on to the next one is ultrasound physics table. As you can see, we have different tissues or material in the body. We have air, fat, blood, liver, and bone. Okay, they have different conductivity of sound. Speed of sound traveling inside them will be different. The more dense and the more dense the tissue, the faster the speed of sound will be traveling inside. And there is also increased acoustic impedance in the tissues and that have different densities, and they have different attenuation as well. Okay, so the more the dense the tissue, the faster the speed of sound, and will have a more acoustic impedance. Okay, so what is acoustic impedance? Is the acoustic impedance is the resistance of ultrasound propagation as it passes through a tissue. Okay, so the faster the speed of sound can go into the tissue, usually the sound will dissipate faster lah. So there is higher resistance to ultrasound propagation. So as you can see here, ultrasound reflection, by knowing this table and the physics of the ultrasound, when we do ultrasound, there is a lot of artifacts that can be produced, which is beneficial to our in our clinical practice in point of care ultrasound. Okay, so the first one is ultrasound reflection. Ultrasound reflection occurs with large differences in impedance between the two tissues. So in the lungs, especially, there is air and also there is a bone, multiple bones, ribs, anterior and posterior ribs. Okay, so when the ultrasound beam is directed towards these two tissues, which have very large differences in impedance, we can have a lot of reflections artifacts. Okay, so these reflection artifacts will cause these A lines artifacts that will be produced by a reflection. As you can see here, from the probe to the first pleural line, and then it will be reflected as a subsequent same distance images will shown as A line. So this is one of the usefulness of ultrasound artifacts in a lung that can be used in lung ultrasound. Okay, so something like mirror image artifact also can be seen when the lung is fully expanded, no pleural effusion, and then you can see the different the liver capsule is very thick and have very different impedance between liver tissue and also lung tissue. So there will be a reflection of the liver into the lungs, which have a lot of air. So lung have a lot of air, and liver capsule have a very dense tissue. So this difference of the impedance between air, a very low impedance, and high impedance in the liver will cause a reflection of the liver image into the pleura. So this is not actually a collapsed lung, it's actually a mirror image of the liver in the ultrasound area, in the lung area. Okay. So this another cardiac mirror image artifact can be seen in the lung. See? Okay. So some other reflection that can be seen is a needle tip comet tail artifact when you insert the guide wire or needle during insertion of the CVL. Okay. So some other artifacts such via reflection, such as ring down artifact, as you can see here, B profile, when there is a column of air in between, inside there is a water in between the column of air. Okay, so ultrasound artifacts also can be produced via refraction. Ultrasound refraction occurs when there is slight differences in impedance between two tissues, such as fluid and also solid tissue outside. So the faster the movement of the sound between faster and slower speed will have the signal refracted, such as usually can be seen in fluid-filled circular structure and the adjacent soft tissue. So this edge artifact is a black lines rising from the edge of fluid structures, such as gallbladder, cyst, vessel, and bladder, urinary bladder. Okay, so this is the gallbladder. So this is a skull of a fetus, also can cause refraction. Okay. So talking about attenuation, slow speed of sound materials that conduct speed very poorly and also material conduct speed very good, such as bone, have a very high attenuation of sound. Means the sound will be attenuated very fast. It will lose its momentum very fast. Okay, so it's a phenomenon when ultrasound wave not propagated further, either fully refracted, such as air, or fully absorbed. It means it's fully absorbed and then it will not be reflected back to the ultrasound probe. Okay, attenuation, when there is attenuated wave and decreased ultrasound signal beyond the tissue. Okay, beyond the air, because it will be reflected very much, and then bone and gallstone means the ultrasound wave is being absorbed, very high absorption. Okay, so as you can see here, renal calculus causing a posterior shadowing, Gaussian causing posterior shadowing. This is a attenuation artifact, meaning there is a very high density like a bone-like structure or stone-like structure and that have posterior acoustic shadowing. Because if there is a structure without posterior acoustic shadowing, that means that the structure is not dense enough, it's not absorbing the ultrasound wave enough. Okay, so this is the example of bone, couple bones, okay, that have a very high acoustic shadowing behind it. Okay, so another one, the last one is a low attenuation structure can cause posterior acoustic enhancement. Okay, you can see clearly in this picture. So enhancement can cause posterior due to the structure that have that can conduct the ultrasound wave very good, such as fluid. So this, when you have a fluid, it can increase the echo window, such as scanning the fetus. So next one, we will talk about echogenicity. Echogenicity refers to how bright, echogenic a tissue appears on ultrasound relative to another tissue. So I make an example here. You can see there is different shades of gray between black and some gray a little bit, and another one is black in this, even in this text. So this is a hyper-echoic, and the tissue appears on ultrasound is hypoechoic. Okay. So bladder is anechoic, clear fluid without any material inside it is anechoic. Think of fluid, blood, unclotted blood lah, urine in bladder, pleural effusion, cirrhosis, and ascites, simple ascites. So next one is pleural line is hyperechoic, means it's brighter compared to the surrounding tissues. Liver is hypoechoic, darker compared to the right kidney. So it's always comparison to one another. Spleen is isoechoic, similar compared to left kidney cortex. So this is the ultrasound terms and terminology that we want to use. So next we move on to transducers. Transducers is the most expensive parts of ultrasound machine. So this is the anatomy of a transducer. In the transducer, typical transducer, you have acoustic insulation at the side of the body, and then you have a backing layer, piezoelectric crystal, and matching layer and acoustic lens. Okay, so when the electric signal is propagated through the probe, and then the piezoelectric crystal will convert electric signal into vibrative acoustic energy into tissues. Okay. Okay, so it will vibrate electric current, and then it will cause tissue waveform generation. Okay, so this backing layer is to prevent backward emitted sound wave into echo and ring back into the transducer for detection. So that means it prevents the sound wave to go to the back and let it goes to the front. Okay, so when the electric signal is given to the piezoelectric crystal, backing layer prevent the ultrasound wave to go backward. Okay, and then matching layer is to provide sufficient acoustic impedance gradient acoustic energy from transducer to smoothly penetrate the body tissue, and it's also function for the reflected acoustic wave to smoothly return to transducer for detection. Okay, so the matching layer, when the ultrasound is reflected back, and it will focus and concentrate the energy into the piezoelectric crystal for the crystal to convert back the energy into electrical signal. Okay. So there are usually in the ICU we use 3 types of probe, which is linear, curvilinear, and phase array. Okay. So when you talk about probes of ultrasound, this is considered the long axis, and this is the short axis. This is in terms of the structure of the ultrasound ultrasound probe. Okay, as you can see in the phase array, there is a square shape, so there is no long or short axis. So there are many different types of ultrasound probe: endocavity, biplanar, intrarectal, and so on. So commonly found in the NS department is this hockey stick, usually used by pain specialists and also regional block. They can use this hockey stick to do procedures. And this is another one some ICU will have, is transesophageal echocardiography. So the first one is to know the indicator on the probe, the orientation marker here. Usually will be correlation with the indicator on the ultrasound machine like this on the left side for all standard application and procedure, and it will be inverted on the right side for cardiac application. So you can see the marker here, usually the brand of the ultrasound. Okay, so the first one is linear probe. Linear probe has a high frequency, and as the name implies, it has linear footprint, straight line, and it is used to produce an image of shallow structure less than 8 cm. It has high resolution and good image quality because of high frequency, but it suffers from the lack of penetration. So it's commonly used for application of insertion of vascular access lines, intraarterial line, intravenous line, central venous line, and so on. So curvilinear probe is a low frequency probe meant for deeper structures. So it can go up to 20 centimeter and beyond, and it have a wider footprint and curve footprint. Okay. So because of the deeper nature of the image, it also designed in such a way to become curved. Okay. So phase array probe is sort of in between these two probes. It has low frequency to view deeper structure, and it also have a narrow footprint. And usually we use it to scan the echocardiography. Okay, and also can use for abdomen. So these three types of probe with three different frequency. So the lowest frequency will be phase array, and in the middle will be curvilinear, and frequency range will be highest will be the linear. Okay, so this is the direction of the sound wave traveling, and this is the direction of sound wave traveling like this, the white body, and then this is the direction of the phase array. Okay, so the different application for different probes as shown here. Okay. So how about suboptimal image? How do you improve imaging of your ultrasound? So suboptimal image, to improve it, the most important aspect is the movement of your transducer. Okay, so there is 5 cardinal movement of transducer: sliding, tilting, rotating, rocking, and compression. Okay, so by knowing and employing these 5 types of movement during ultrasonography, you can improve the imaging of your structure of interest in any application that you want to use. Okay, so first one is sliding. When we talk about ultrasound movement, we can say, okay, slide the probe up and down, or left or right. So this is the usual terminology that we want to use. Okay, number 2 is fanning or tilting. You can tilt like that, okay, to produce a different image. You can see, yeah, you can produce different image when you tilt. And then the rotating, you can rotate and to have a different short or long axis of the vessel. And number 4 is rocking, side by side, rocking along the long axis. When you say rocking, usually we rock along the long axis. Okay, that it can produce a very different image and direction of the plane of the ultrasound image. Number 5 is compression. Usually we want to differentiate between artery and vein. Compression, like simply compress the tissue with your ultrasound probe. So another thing that you need to know is that plane of ultrasound. So one is cranial-caudal direction. When we say more cranial, it goes towards the head. More caudal go towards the leg. Okay, and then there is the multiple plane of imaging of the body. Sagittal plane like this, cut in between to the left and right of the patient. Coronal plane will cut between the front and the back of the patient, anterior and posterior of the patient, and transverse plane transversely along the body of the patient. Okay, so when we talk about scan in transverse plane, more in the cranial direction. So transverse plane, the ultrasound probe will be like this, and then cranially it goes up towards the head. So more on the another one is the orientation of the structure, long and short axis orientation. Especially when we talk about structures in the body, such as the vessel. Body structures can be viewed in multiple angulation and multiple direction in whatever way you move the probe. Okay, so probe orientation will produce the underlying structure slicing image of the body structure. Okay, so as you can see here, this is a short axis. When we put the probe like this, when we rotate the probe and become along the lines of the vessel, it will become long axis or longitudinal. If we put the ultrasound probe like this, it will cause a slightly oblique oblique picture, and the vessel will not be fully round like this. It will be more of pear shape, okay, which means it's an oblique view or slicing of image of the structure, oblique orientation. So we usually use and try to find either short axis or long axis. Okay, so this is the direction of the probe, and this is the what you see in the image of the ultrasound. Okay, so if you put it along the longitudinal axis of the vessel, you can see the longitudinal axis or long axis structure of the vessel like this. Okay, so long and short axis orientation of a body tissue usually we can use also in the echocardiography like this. If you can see short axis of the heart, when you scan like this, you will scan the short axis of the heart, and if you point it towards the the right shoulder, it will scan the long axis of the heart like this. Okay, from the apex to the base, long axis. And then for short axis of the heart, you can have multiple views by moving the ultrasound probe craniocaudal direction, and even by tilting the ultrasound to see different structures such as at aortic valve and also at the papillary muscles area. Okay, so the last thing about orientation of the probe is that whenever you turn the probe into any different direction, you have to remember the probe will only convey the image to you as the direction of the ultrasound. If you put the ultrasound straight like this, okay, it will produce an image exactly this block and slice of images. It will not show the other parts here and here. Okay, so likewise, if you put the ultrasound probe obliquely like this, tilting fanning like this, it will cause the block and slice of images to be sent to you in this direction, in this block slice of direction. You have to have a mental image on how the direction and plane of the ultrasound image will be sent to you when you're doing procedures. So if the ultrasound probe is tilted like this, so of course the images will be longer section, and then you can see the structures in this image and this point of direction. Okay, so you have to understand this image of the ultrasound we will produce tilted like this and straight like a block. The block of slice of image will come to you this direction, exactly at the beam of the ultrasound traveling through. Okay, I hope you understand what I mean. So the next one is the modes of ultrasound. Ultrasound have many different modes. So they have B mode, M mode, color Doppler. So B mode is the brightness mode. It's the most basic mode, which is the main grayscale baseline mode for ultrasound imaging. Some manufacturer like Sonosite and Philips use the term 2D mode, and BK also use 2D mode. So if you get lost in other different modes, you're pressing M mode, color Doppler, or whatever Doppler, then you are confused and get lost, you can just press back the B mode button or 2D mode button to reset everything and go back to square one. This is a normal B mode. So what about M mode? M mode is a special mode. It's also called as a motion mode. It's a motion versus time display of the B mode ultrasound image along a chosen line. So once you have chosen a line in the B mode like this, okay, only on this exact line it will cause this slice image on in a time manner. Okay, so y-axis will be the motion and x-axis is time. So as time move on, you can see at that specific point on what is happening to the structure. Okay, common application of for M mode: E point septal separation in cardiac scanning, calculating fetal heart rate for obstetric, lung ultrasound to evaluate flows, lung sliding and rule out pneumothorax, and also probably IVC variability index. And M mode simply takes a slice of your B mode image where the crystalline is placed and translate that slice over time. Okay, next one is Doppler modes. Doppler is the ultrasound mode studying fluid shift and fluid movement in relation to the ultrasound beam. Okay, so when you beam the ultrasound in the vessel, there is also a movement of fluid. So when there is an angle insonation, it will study the fluid shift with regard to the ultrasound beam. So angle of insonation is extremely important in what the transducer will detect as a speed of flow or movement. For any type of Doppler, you want the flow movement to be going directly towards your probe or against your probe. Okay. As you move towards a 90-degree angle, there will be no flow detected by the ultrasound machine. Maybe you can remember that you can see something, some vessel, but when you put on the color, there is no color. Okay, so when in the vessel, when the flow is going towards the probe, it will show as a red color. When the flow is going, or the blood vessel going away from the probe, you will show a blue color. So that's why when you put at the longitudinal axis, and then the ultrasound, when the flow of the vessel is perpendicular, sorry, not perpendicular, is the same, exactly parallel to your ultrasound beam angle, he will show as black. Okay, perpendicular equals to black. Okay, so color Doppler mode is the most commonly used in the Doppler mode is the study of the movement of fluid inside the structure. Color Doppler mode is the most commonly used Doppler mode. Red does not mean arterial, blue does not mean venous. So it's mainly showing the direction of the flow in relation to the probe. So power Doppler image is more sensitive color Doppler mode, not available in all machines, and unable to tell direction of flow. It only uses a single color spectrum to indicate amplitude of flow. And pulse wave Doppler mode, all other Doppler modes use the same principle of Doppler shift over time. Positive reflection above the baseline indicate flow moving towards the probe and vice versa. Okay, so positive reflection above the zero, negative reflection away from the probe is below zero. Okay. So last one is ultrasound knobology. So to know the ultrasound of different brand have almost similar setting and setup. You know, you can along your career you've seen a lot of different ultrasound. Okay, ultrasound different brands have almost similar settings and setup, although buttons can be placed at different place in different ultrasound machine. But the knobology wants to teach you about the same steps and things that you need to know when you're starting to use ultrasound. Okay, number one is, of course, you have to know where is to power on the machine. You have to identify what is the universal power symbol, button symbol. It's a binary symbol of 0 off and 1 is on. So when they combine, you can get the symbol like this. This is a universal symbol in all ultrasound machine. In fact, in almost all other other medical based device as well. Number two, you have to know how to switch the transducer. You need to know how and where to switch the transducer between the 3 transducer probe. Okay. Number three is to check all the presets available provided at the application preset. Number four is to adjust the depth according to your area of interest and what you want to scan. Number five is to adjust the gain, overall gain, to improve contrast of imaging, which can help for you during your imaging study. Number six is time gain compensation. Contrast can be adjusted in the near or far field of image according to your area of interest. So number seven is to look to focus the ultrasound beam to improve the image quality at the place that you want to insert, like a focus on the vessel and so on. Okay, so you can have a very specific depth which you can improve the image quality. Number eight, you have to know where to freeze an image capture. Okay, number nine, and the last one is you have to know how to do some basic measurement and where to find the buttons. Number one, power on. Step one is to on the machine. Okay, obviously you need to on before you can use. Power on button is a universal symbol. It's the same in everywhere, all the ultrasound machine. usually at the topmost position. Most ultrasound place button at the topmost position, either on the left or the right. Okay, if the normal laptop ultrasound, usually at the top of the keyboard or button, but like this lah. Okay, left side or right side. So, but some machine likes to trick you. They place the power button at the sides of the body or at the back of the screen. Okay, depends on what the ultrasound company wants to do. Okay, so like this BK ultrasound, one type of BK is behind the monitor, another type of BK ultrasound is the side of the body of the ultrasound. So you have to know how to switch between the ultrasound probe. As in the GE venue, you can look at the top right of the screen. They show here the different type of transducer probe, and every machine have its own way of changing the probe currently activate to use. Mostly have independent button for each transducer to activate it. Some of the machine will have a button to alternate between probes to be activated. Okay, it's like this. Okay, so you have to press like BK ultrasound is on the panel down here, and then you can choose the transducer by clicking on the transducer, and then you choose what transducer probe that you want. Okay, the third one is application preset. Most of the machine will have application preset that have optimally designed to have ideal frequency, depth, and gain for the specific purpose of scanning. For example, phase array transducer will shift and invert between the image between abdomen and cardiac. Thus, the marker will be on the left of the screen. So if you choose abdomen, the marker will be on the left of the screen. And if you choose cardiac, the marker will be on the right of the screen. Okay, depth and gain will be more for abdomen as a preset compared to darker and shallower for cardiac preset. So the manufacturer have designed in such a way that different preset will have the best optimal imaging gain for the study. So like this, you can choose between vascular, cardiac, and abdomen. So next one is the number 4 is depth. It's very important. When starting scanning, adjust the depth of ultrasound just enough to see the structure of interest. Too much depth will let wasted of ultrasound real estate. You want to see the top part, but you put the depth too much down here, you will lose it because you don't want to see anything down here. So you will be wasted ultrasound real estate lah. So upon adjusting the depth of the ultrasound screen, the numbers in centimeter will correspond to the depth of the penetration. Okay. So as you can see here, this is how to adjust the ultrasound depth in venue. And for the logic ultrasound and other ultrasound, you have a knob here you can use to adjust the depth of the ultrasound. So for BK, there is also a knob there. You can turn and adjust the ultrasound depth. So next one is the most popular knob in the ultrasound machine is that after that you should adjust your ultrasound gain to improve contrast or brightness of ultrasound image. It is simply an overall adjustment of brightness or darkness. Too little gain will lead to darker image that makes it difficult to appreciate the structure of interest. All right, as you can see here, under gain image is too dark, you can't see all the structures and how you want to insert vascular access with an image like this. Okay, how you want to interpret anything if the image is very under gain, too little gain. Too much gain will lead to unnecessary artifacts, reflection, refraction, and sometimes obscuring hypoaquate structures surrounded by hypoaquate structures. So overgain image like this, sometimes there is a small vessel here. When you put the gain too much, it will obscure the small vessel right beside it, and you can't see it because the artifact, refraction, reflections all are too much and until obscuring the small hypoaquate structure. Optimal image is not too much or not too little. This is what we want actually in life for everything. Optimal, not too much or not too little. So you can adjust the gain here in the BK ultrasound. Okay. So next one is a TGC, time gain compensation. Instead of adjusting overall gain, most ultrasound machines allow gain to be as specific only at level of depth required. Okay. Depending on specific application, TGC can be useful to highlight or dim separately between deeper and nearer structure in relation to the probe. Two types TGC exist. Most use multiple level gain adjustment control and some use few points level of gain control as the picture shown here. Okay, so for Sonosite, they have 3 level, the basic Sonosite and the older version have near, far, and overall. Okay, so near gain will be the near field gain here, and far field gain is here. Okay, so the far deeper structure gain. So if you turn it down, it will be darker only at the far field, and if you turn it down, it will be darker only at the near field. Okay, so most of the ultrasound have different, very specific level. Okay, as you can see in the picture here, if you decrease the middle level here, TGC, it will be black just in the middle, but the near and far field is very brightly light up. Okay, so as you can see here in the BK ultrasound, you adjust the gain, you increase the near field gain, the near field will be bright, but the far field will be black, will be black. Okay, so if you turn it the other way around, the far field will be bright, and near field will be black. So next one is the to adjust the focus. Okay, improving image at specific level of depth also important to improve accuracy and resolution at specific place. This is more so important in vascular access. Most machines have this feature as it will concentrate ultrasound beam at a specific level to improve resolution. It is advisable to adjust the level of focus at a specific depth of interest. So usually, if a regional anesthesia, you want to, like, for example, supraclavicular block, you want to see exactly nicely the bundle of nerve, bundle of grapes. You can adjust the focus right at that point only, right at that level. So this is the focus depth. You can move up and down for venue ultrasound. And for the BK ultrasound, you can turn up and down where at the depth you want the focus to be more increased. So the ultrasound beam will be focused on that part, and will try to improve the image at that point of the image. So second last one is you will have to know every machine will have its own freeze button, which is universal for all machine. The symbol for freeze will be different, but everyone have freeze button. Okay, so freezing image will allow us to stop and study and measure the image. Usually freezing allows us to review clips for a few seconds prior to the frame frozen, and image capture can be done in certain machine, and storage of video clips also possible if the time management is available for the machine. For venue, you can even store clips of 6 seconds, 5 seconds, depending on your setting. And when you press freeze, it can also store the store means you can store, if you freeze and then you store, then you store the image. If you don't freeze, you can store the video clips of the image. Okay, so like freeze in this ultrasound example here. Last one is the measurement. Each application preset will come with its own specific measurement. Common to all is Caliper, which is simply measuring the distance between 2 points of the ultrasound image. Certain measurement only available in specific preset, such as measure biplane volume for LV, and diastolic and systolic for ejection fraction measurement. Like here, will be available in cardiac preset and cardiac probe. Advanced tool using Doppler measurement will also be available, such as pulse wave Doppler, allowing us to measure the speed of volume ejected, or maybe during measurement of cardiac output. Okay, so as you can see here, press the measure and the menu will come up. And then for venous ultrasound, you can use this to click and release and click for the measurement. So for basic ultrasound laptop base like this, you can press measure, you use the mouse to roll over the screen, and then you can press set. Okay, so that's all from me regarding basics for ultrasound. Thank you. Have a good day.